All right, we'll go ahead and get started again. Our last speaker of this session is Fei Zhang. Fei is the technical lead in scientific computing at Geoscience Australia, and today he's going to tell us about geoscience big data computing with Python.
Good morning, everyone. It's my great pleasure to come to PyCon and give a talk. So, me and my colleagues are regular attendants of PyCon. My first time come to PyCon was 3 years ago in Hobart, and this time I thought I might give a talk. So I proposed a talk and then got accepted. So that's why I'm here to give this talk. So this talk is about geoscience big data computing with Python. Just interested, how many people knows about Geoscience Australia? Oh, there's quite a few. Very exciting. So Geoscience Australia, this is outline of my talk. First, I'll give an introduction about Geoscience Australia, and then I will talk what kind of data sets we have and what big data challenge we have in Geoscience Australia. Then I will focus on Australia Geoscience Datacube. It's a system that has been developed in the past few years. So there's a story about how Geoscience Australia Datacube is constructed, developed. And then I will have some time to do some live demo using Jupyter Notebook. And then I'll give some concluding remarks. So here's about Geoscience Australia. I better use our official description. This official description actually changed over time. So this is the current one. You can find from the website. Geoscience Australia is Australia's preeminent public sector geoscience organization. We are the nation's trusted advisor on the geology and geography of Australia. We apply geoscience and technology to describe and understand the Earth for the benefit of Australia. So this is the exact quote from our website. And more specifically, our core business and strategic priorities, including 4 areas. The first one is secure Australia resource. That's the first image you can see. We help to discover where the minerals, where the energy is petroleum, and through doing surveys and collecting data, providing pre-competitive data to industries and partners. The second priority area is the community safety. Using earthquake detection alert, tsunami warning system, using satellite imagery to do the bushfire monitoring, bushfire detection. So that's the community safety. Then is secure Australia water resource. Water resource is a very precious thing, and Australia continent is dry continent, relatively dry continent. So we need to know where are the waters and how the water's surface and groundwater interact and to find all the water resource. And this one is about managing Australia's marine jurisdiction. So we not only study and manage the Australian continent, but also its surrounding marines. And this is geography knowledge. So the geography is about road, about buildings, urban areas, all the features, rivers, so the mapping. We have all sort of mapping of Australia. And last one is about geodesy, or Australia geodesy network, all the data collection networks, infrastructures. So that's a brief introduction of Geoscience Australia. And As so many people already know about Geoscience Australia, it's in Canberra. It's a very nice building with a free parking on site, and there's a very nice visitor center, and you can see a lot of rocks and minerals and petroleums and even gold nugget in the foyer. So if you have time to come visit Canberra, come to visit us, and it will be very interesting. So scientific computing system and system engineering is a section within our ICTA's innovation branch. And Python is the main programming language, very broadly used in Geoscience Australia. So I'm very happy to share this with you. Basically, Python is being used in data acquisition and engineering systems. So when the data collection in the networks, in the seismic networks, satellite ground station, we all use Python to control the data collection systems. So then when the data is collected, we need to process the data and analyze the data. Over the years, you have many data, a lot of data. We have used Python to manage the data archive. And then scientists can use data to do modeling and predictive analytics. And all this computing, actually it takes a long time to run in an even supercomputer. So we need to use workflow automation. This is, again, a lot of workflow automation is done in Python programming language. And also recently we have a team dedicated to cloud computing, which use Python to do infrastructure as code to spin up Amazon EC2 clusters. So it's all done in Python. So we are by far perhaps the biggest Python shop in Canberra, at least in the public service sector. So we basically use Python everywhere, in people's PC desktop every day, Linux servers, cloud computing infrastructures, and HPC environment. So where are the big data in geoscience? Basically, there are a few areas I can highlight here. One is a satellite imagery time series. We collect satellite every day, virtually every day. When satellite pass through Australia, we have a ground station in Alice Springs to acquire the data broadcasted to us to the ground station. So that's done every day over the past nearly 30 years. And the second area is seismic survey data collection. And the bathymetry survey data. Recently, the MH370 airplane is missing in the ocean, so we had a program to acquire lots of the ocean bathymetric data, try to discover where the plane landed. So that's a big data collected and archived in Geoscience Australia. So all that, and also like point cloud, digital elevation model, GIS mapping, geodesy, boreholes. So altogether, Geoscience Australia has a data holding exceeding 2 petabytes at least. And this number, of course, is growing every day. I say 2 terabytes is a conservative estimation. Today, I'm going to focus mainly on the area of Earth observation, satellite imagery data. So there are 2 primary ways of obtaining Earth satellite imagery data. One is called the so-called real-time, and data acquired at the ground station. Geoscience has a ground station in Alice Springs. Alice Springs is a place in the center of Australia, so its ground station can cover pretty much everywhere of the continent when satellites fly just over Australia. The other way is through the non-real-time systematic download data from the satellite operators, operation agencies, such as the United States Geology Survey and other European Space Agency. These are launch satellite, operate satellite. They have set the satellite data acquired through relaying. So yeah, so we also download a lot of data from there. So this animation just show you the satellite orbiting around Earth. When it passes Australia, it will acquire imagery, and that is the satellite imagery we are talking about. So the satellite actually orbits Earth very fast. It's one round is about 100 minutes, and Earth is self-rotating. So this couple dynamics makes this kind of satellite footprints on Earth, and you see that's a path or two paths, and that's the image we deal with. And the Earth observation big data sets, and it's actually, as I said, we begin to acquire satellite data since more than 30 years ago, and it's gradually increasing. And in recent years, it's actually, there's a huge jump because of new satellites and more high quality, higher resolution sensors. Previously, we have, for example, satellite Landsat have 30 meters spatial resolution. Nowadays, with the Sentinel series, Sentinel 1, 2 series, you have 10 meters resolution. So the higher the resolution, the more data you will have. And also the spatial resolution, the temporal resolution increased. There's a Himalaya 8 satellite, which is a geostationary satellite, which stay on the space relatively stationary to Earth and taking imagery every 10 minutes. That way you can monitor in the Earth bushfire, all the natural disaster happening. Every 10 minutes you can have a satellite imagery. So I mean, people from BOEM are very familiar to this kind of satellite imaging. And although, yeah. So a huge change took place in the past 10 years. I joined Geoscience Australia 11 years ago. And at that time, satellite data was processed on user's request. Was processed by operators manually, delivered on tapes, DVD, CD, sometimes FTP sites. It cost quite a bit of money to the users. And we used to, when I first came, I heard that we have $1 million revenue from selling satellite imagery. And nowadays, it's no longer this case. So because the advance of technology, the entire data archive is pre-processed into calibrated, high standard analyzed ready products and stored online in petabyte scale file system, freely available to all users under a Creative Commons license. So this gives birth to Australia Geoscience Datacube, and I'm going to focus there. So AGDC is basically an innovative solution to the big data challenge in Earth observation space. In this area, our organization actually is leading the world, and other world space agency organizations like USGS, European Space Agency, they all come to use, collaborate with us and use the ideas we have developed, the system we have developed, try to do their problem. So we are leading this area. And the system manages a deep time series of Earth observation archive data, covering 30 plus years and the whole Australia continent. This continent. Previously, 10 years ago, basically people only study one area, one particular area. But nowadays, we study the whole continent with satellite imagery. And the system provides the API to enable users to explore, search, retrieve, analyze the big data sets. And I'm going to give a demo later. So, and basically it enabled the development of a wide range of applications. And the system, of course, developed by, with Python as the main technology. It's quite surprising, maybe. And here, quickly show you this video. It's starting. OK, give people some kind of idea what satellite imagery look like. When satellite pass Australia, it's basically take image along its footpath, and then over a period of time, you will cover the entire continent. In the case of satellite Landsat, it takes 16 days to cover every area of Australia. 16 days revisiting cycle. And so, over many years, we will cover the continent many times. That's why we have a time series. And the Australia Geoscience Datacube is basically organize this archive and organized in a particular, quite smart way, divide all the imagery data into cells. In this case, first version is 1 degree by 1 degree cells. And currently we're using a different projection called Arbus conic projection, which is 100 kilometers cells. So it's like database partitioning. This database is petabyte scale. We partition it in space. The advantage of doing this is when you partition your data already in space, people can search it, retrieve it very quickly, easily. So that's the idea of database management system applied in a spatial temporal context. So basically, that's a video to show you the Datacube. Continue. This system is actually many years in the making. Started in 5-6 years ago with a project which I was deeply involved. It's called Unlocking Landsat Archive. Basically, this is a multi-million-dollar funded project because people see the potential of this archive data. So they fund the project to process, let's process 10 years of archive, 10 years archive from 2010 to 2000, from 2000 to 2010, and then make it available to all users, communities. So that was done, and basically done over exceeding the stakeholders' expectations. They wanted us to process 10 years. We actually processed 12 years. So it's on time, on budget. And basically, it was done with the help of National Computing Infrastructure, NCI at ANU. That's basically is a collaboration partner in this multi-million-dollar project. And we were using not even the last generation supercomputer, which was Vayu, I think. Currently uses Region. And we needed to set up a special Linux cluster to process the over 100 terabyte of data. And that because of that time the software was written not ready to be used in supercomputer cluster. It had to be a customized build cluster. And I wrote lots of Python script to automate workflow, and even that took a lot of time and pain to process the archive. But it was done with the help of power of Python automating things. And basically, you let the computer cluster running days and weeks, about 3 months' time to process the archive. Technology used in the AGDC Python modules, I would like to highlight this. This is not exclusive list, but the major Python modules like GDAL, raster.io, the shapelet, GeoPandas, NumPy, SciPy, the major workhorse. We also use SQL allows me to connect with database, backend database, Postgres. NetCDF is a major file format we are using currently, and the visualization, Jupyter Notebooks, X-Array, and Dask. My colleague Andrew Hicks will give a talk on X-Array and Dask in the afternoon. It should be very interesting. So at this point, I quickly knocked up this architecture to show you that the process flow, the structure of the AGDC Datacube. And basically, how we do the Datacube is that starting from here, raw data sets, this is the archive data, and that have to be processed into standard imagery data and then ingested into the file system. And the file system of the data files, the imagery, have to be indexed, and the index stored in the Postgres database tables. And then we have a package of Python modules we call native API interface to allow user to search and retrieve data from this data cube. And then you do all your kind of applications, whether it's detect water, or whether you want to do any kind of vegetation land cover change applications in the standalone programs, or in batch jobs, or using interactive computing with, for example, Jupyter Notebook. Then you produce some derived products, digital products. You can publish it, and you can ingest it back into the Datacube system. Then other people can retrieve and use it. They don't have to derive it again. So that's the overall structure and workflow of Datacube. Now, demo time. Okay, so I think. So this is a Jupyter Notebook. I'm not running it in my own laptop. This notebook is running in NCR infrastructure, and I just remotely access it. The way to access it is I have to use a SH client to log into the system, use a tunneling method, so that I can use local host actually accessing the NCR infrastructure. And I also would like to, as a side note, there's some security issue with the Jupyter Notebook. Once it's running in your own laptop, it's fine, no other people access it. Once you are running in a shared server, the default Jupyter Notebook running in port 8888 actually can be accessed by other users, just like yourself. So best to use a secure mode, which is you have to set up some HTTPS secure accession and set a password. In this case, you see I have a logout button. This is because I have logged in beforehand. And okay, so security thing, just remind people, otherwise people access it just like you can't do anything. So demonstration, this is a notebook. First thing is basically I can have an image inserted into here, run it live. You already see this picture, it's about architecture. And some references about, we have GitHub, have a look of Geoscience Datacube GitHub, and a lot of open source repository there. And computing, basically the first thing is to import some Python modules, whether it's SciPy, what's happening? Whether it's SciPy or NumPy. And in this case, I also dynamically insert a path, which with AGDC version 2 source code here. So this is another feature of Python, allow you to set a dynamic import path. So that's successful. Then I begin to have a data access object, construct a data access object. And you can see with this, what you can do is to, you can list the products stored in the Datacube. This is real Datacube behind scene. And so I'm going to run this cell, list all the products stored in the Datacube. And here I just list the first few. If I let it all go, it will have 100 of lines. And the measurement is about the satellite bands. Satellite imagery in a simple sense is like RGB image. It's related to the electromagnetic waves. The sensor is trying to acquire data. So this list all the satellite, different satellite band, that blue, red, blue, green, and blue, all the band. So some basic information about the satellite imagery, the data stored in the Datacube. All right. And the next cell, okay, I'm going to focus on a spatial temporal extent. Spatial is defined by the longitude and the latitude. This area I choose come from cover the Canberra region, and because I want to show you the Canberra Lake Burley Griffin from satellite imagery. So with a temporal period of basically 2015, and I'm going to do the Landsat 8, which is the newest Landsat series. We have Landsat 5 already out of service after 25 years in the space. Landsat 7 is really have some issues. Landsat 8 was launched 3 years ago, maybe. So it's the newest. I run this cell. This may take up to 1 minute, because it's going to the Datacube and retrieve 1 year data archive, covering that space of Canberra region. It's already done very fast, okay. And this is basically the data. As you can see, this retrieved data is X-array data set, and it has time dimension of 75 slices of satellite imagery with X and Y dimension, basically latitude, longitude, is the spatial grid. And all the data sets include green, red, near infrared, shortwave infrared. All those is terminology of satellite band. So I don't have to show you these things, basically. Okay, so with this data set, you can look at what's the minimum time, what's the maximum time. As we are interested in the year 2015, it starts from January, and the last scene is basically in November 26th, okay? So that's what's in the Datacube. All right. To show you some real satellite imagery here, and is this I made this function to retrieve RGB imagery as individual slice. And I basically define a function. In a Jupyter notebook, I think it's a good practice also to define some functions instead of repeat every time. So I just define a function called show image. Run it, yes, done. And then I can use this function to show an image. This one, show the first image. That's red, green, blue. That's satellite image. Okay, and next one is scale the image. I'm going to show you a color image. That one make a RGB image. This one is more interesting. Is it? Oh, this one, okay. This color image will clearly show you the camber region and, okay. So you see the lake polygraphing? I mean, whether it's clear or not. From your perspective, yeah, that's the camber region, that's RGB image. All right. Okay, yeah, so the demonstration is here. If people are interested in more things, you can come to me and I can show you. This is the available time, okay? It's because it's running in the NCI supercomputers. So to wrap up my talk, because of the time, let me just quickly go through some slides. Lots of applications can be developed on the Datacube. And I would like to acknowledge really our partner collaborator, NCI. They provide supercomputing. And CSIRO and other organizations collaborating with us on this Datacube system. Concluding remarks, we basically talking about software development in this kind of scale. We need to have some good practice. Here's a use GitHub, of course everybody know, continuous integration, unit testing, and source code documentation to manage the system. So in summary, Python has been successfully used in geoscience big data problems. It's a really big data, or petabyte scale. I mean, it's increasing. Python is very suitable for geodata computing, from geography to seismic, geology, geodesy. Every area in Geoscience Australia, we use Python. And we have geodata modeling, geostatistics, machine learning, predictive analytics currently going. And in geoscience, Python had a bright past. I have been there 11 years, so no problem. I can testify that. And it looked like it will have an even brighter future. So, lastly, what is the bright future? AGDC, Australia Geoscience Datacube, currently continues to be an active, high-priority program, well-resourced, with a strong team of Python developers doing the heavy lifting. The long-term objective is to develop the AGDC system into an integrated geoscience big data framework where we can develop things like integrated Earth, all kind of integrated there, allow people to analyze where the resource, what is where on the Australia continent, and the virtual geophysics laboratory, which will be interesting to all kind of user research community to bring your own algorithm, plug in, and use the real data to predict or analyze to see the changes in the geoscience. So with this, I end my talk. Thank you.
Okay.